Okay, so this lesson is from day 2 of trig. So we're going to be looking at the reciprocal trig functions and radian measure for angles. So in the last lesson, we ended by defining the trig functions as ratios of x, y, and r. So that we could look at the trig functions as the outputs as ratios of values of x, y, or r, where x and y are just points in the Cartesian plane, the xy plane, and r is always the distance of a point in the xy plane to the origin. So before we look closer at this, I just want to remind you of quadrant 1 in the unit circle. So let me kind of sketch that. And how we can extend our knowledge of the unit circle to look at the trig functions being defined as these ratios of x, y, and r. From geometry, you guys were familiar with looking at the trig functions and thinking about angles as being the input values, as we are now. But then the outputs were ratios of the right triangles, right? SOHCAHTOA, like sine of an angle theta was equal to the side opposite. So thinking about the right triangle, so the side opposite that angle over the hypotenuse of the triangle. Cosine was of theta would have been the side adjacent to that angle theta over the hypotenuse. And tangent would have been the side opposite over the side adjacent to that angle theta. That was pretty limiting because all of those angles, to be angles in the right triangle, had to be acute angles, angles that are less than 90 degrees. So now being able to define the trig functions as ratios of x, y, and r, so values that we can find in the Cartesian plane, this will allow us to evaluate trig functions for any angle, which is pretty cool. So again, let's look at quadrant 1. So let's say that this is the unit circle just in quadrant 1. I apologize for my portion of that circle. Okay, so one point that we know lies on the unit circle is the point root 3 over 2 comma 1/2. And we remember from the other day of deriving the unit circle that we found that point, the ordered pair for that point, by constructing a right triangle in the unit circle. So we dropped a perpendicular down to the x-axis. Okay, so here's our right angle. This angle would be 30 degrees, this angle 60 degrees. And because we are looking at a unit circle, we know the radius of the unit circle is 1. Therefore, the hypotenuse of the triangle was 1. The side opposite, 30 degrees, is 1/2, and we derived that. And then the side opposite, 60 degrees, would be root 3 over 2, which is how we got that point, root 3 over 2 comma 1/2. Okay, well, let's think about the idea of similar triangles again, or similar right triangles. So if we were to multiply each side of this right triangle by 2, we would end up with a point out here, where this point would be root 3 comma 1. Okay, if I drop a perpendicular and think about constructing a right triangle, the hypotenuse of this right triangle would be 2. So Miles asked a great question last time. He said, well, why don't we use a circle with a radius of 2 to use as our reference, so that the points on the circle will be like root 3 comma 1, root 2 comma root 2. But the reason we want that radius to be equal to 1 is that we can easily look at just points on the unit circle and know the values of sine or cosine. Because let's think about this. This angle here is still 30 degrees. So if we wanted to find sine of 30 degrees, okay, by referencing our pink right triangle here, so this would be 1, and then this would be root 3. So sine of 30 degrees, thinking just SOHCAHTOA, right? Opposite over hypotenuse. So the side opposite would be 1, and then the hypotenuse would be 2. So we'd get 1/2, which we know is also the y value on the unit circle. Or cosine of 30 degrees would be adjacent over hypotenuse, so that would be root 3 over the hypotenuse of 2, which, well, we know also that that is the that is the x value on the unit circle. So you guys, we can basically, for any point that lies in the xy plane, we're going to be able to evaluate, or I'm sorry, for any point in the xy plane, if we know what x, y, and r, the distance of that point is to the origin, we can determine different values for different trig functions, right? Trig functions evaluated at different angles. We don't even necessarily need to know what an angle theta is. Okay, so you guys are familiar with sine, cosine, tangent. Sine is y over r, and the unit circle r is equal to 1, so that's why we're able to just look to the y value of each point on the unit circle to determine what sine of theta is. Cosine of theta is x over r, and again, since r is equal to 1 in the unit circle, that's why we can just look at x on the unit circle to determine cosine of theta. And then tangent is the ratio y over x, and that's also because tangent of theta is equal to sine of theta over cosine theta, and we also talked about that the last time. Now, these three trig functions underneath sine, cosine, and tangent are the reciprocal trig functions. So this first one is cosecant. Okay, the next one is secant. And then we have cotangent. Okay, so cosecant of theta, let me go to the next slide. So cosecant of theta is actually equal to 1 over sine of theta, meaning it's sine's reciprocal trig function. So since sine is equal to y over r, cosecant is equal to the ratio r over y. And secant of theta is the reciprocal of cosine, so its ratio is r over x. And then cotangent is the reciprocal of tan of theta, and its ratio, therefore, is x over y, but also cosine theta over sine theta. Okay, so radian measure. So up to this point, you guys have really just talked about angles that have been measured in degrees. And degrees is wonderful. We're going to use degrees again when we talk about vectors. And we'll use degrees for different applications. But in calculus, especially, you guys are going to want to use radian measure for your inputs of the trig functions. And radian measure is cool because it's actually unitless. And here's why. So if we have, let's look at this circle here. Okay, so the circle has a radius of r, and it has an arc length that we're going to call s. And you want to know this because I have seen SAT 2 questions related to radian measure, and you should know what arc length is, and you guys already should know what the radius of a circle is, how to determine the radius of a circle. Okay, so S is equal to arc length, and then R is the radius of the circle. So if we want to know what this angle is here, theta, we use the Greek letter theta to represent angles often. Theta is equal to the ratio S over R, so arc length over radius. And arc length and the radius must be in the same units. So when they're in the same units, like if both are in feet, if both are in centimeters, whatever the units are, those units will then cancel. And then when theta is measured in radians, what we call radians, theta is really unitless. It's just a real number, which then will allow us to write the trig functions, or represent the trig functions in the Cartesian plane, right? Because in the Cartesian plane, the x-axis and the y-axis are both real number lines. So this will allow us to actually graph sine, cosine, tangent, and the reciprocal trig functions in the xy plane. Now, I know you're probably a little bit confused me saying that, because the unit circle is we're thinking of it as being in the xy plane, right? But the unit circle is not the graph of the trig function. It's not the graph of sine. So having our angles being in radians, we could graph, for example, y equals to sine of x, where x represents the angles that are the inputs, and x is, if it's just in radians, then it's just values that are on the x-axis. And then the output could be y, which we know how to determine those ratios now. That would be the outputs. And I have a cool little GIF. This is a PDF, so I can't show it to you, and it didn't work when I tried to show it to the class, so I'm going to try and find one that does work and email it out to you guys. But it's just a cool little video or image, visual of what radian measure is. Okay, so the circumference, just a reminder, the circumference of a circle is equal to 2 pi r. So if we have a circle, okay, here's my xy plane. Okay, and then let's think about an angle theta that's a full rotation. Now you guys know from us deriving the unit circle, a full rotation is 360 degrees. So what would the arc length be for an angle that is 360 degrees? Well, it would be the circumference of the circle. So arc length for this angle theta S would be equal to 2 pi r. So then if we wanted to figure out what theta in radians is for the angle 360 degrees, well, it's S over R, right? So S being 2 pi r over the radius. So those r's would end up canceling. So 360 degrees is equal to 2 pi. So full rotation is equal to 2 pi radians, or 2 pi rads, or we can just say 2 pi. So now we're going to fill in the unit circle, the remaining portion of the unit circle, which is angle measure in radians. So 0 degrees is equivalent to 0 radians. 360 degrees we just proved is equal to 2 pi radians. So a half rotation would be equal to pi. Okay, so that's just half rotation is pi. Okay, so 30 degrees is 1/6 of 180 degrees. Therefore, 30 degrees is equal to pi over 6. And notice if I add another 30 degrees, or I add another pi over 6, that puts me at 2 pi over 6. Add another pi over 6, that put me at 2 pi over 6, which is equivalent to pi over 3. So if I add another pi over 6, so 2 pi over 6, 3 pi over 6 is equivalent to pi over 2. 4 pi over 6 is equivalent to 2 pi over 3. 5 pi over 6, where you have 6 pi over 6 is just pi. 7 pi over 6. 8 pi over 6 is equivalent to 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 would be 5 pi over 3. Okay, and 11 pi over 6. Now notice that 60, I'm going to skip 45 degrees for a second, but 60 degrees is 1/3 of 180 degrees. So if we had pi over 3, add another pi over 3, that'd give me 2 pi over 3. Another pi over 3, that's 3 pi over 3. 4 pi over 3. 5 pi over 3, and then 6 pi over 3 is 2 pi. So 45 degrees is 1/4 of 180 degrees, so pi over 4 is 45 degrees. 2 pi over 4, 3 pi over 4, 4 pi over 4 is filled in, 5 pi over 4, 6 pi over 4 is filled in, 3 pi over 2, 7 pi over 4, and then 8 pi over 4 would be 2 pi. So those are the angles that are on the unit circle in radians, and you also now need to memorize those. Let me rewrite pi over 3. Okay. So this is what you need to memorize to fill in for our big unit circle quiz that's on Friday. Okay, so for converting between degrees and radians and going degrees to radians or radians to degrees for angle measure, since instead of setting up a proportion every time you want to convert from degrees to radians or radians to degrees, you can do these shortcuts. So if you want to go from degrees to radians, you can multiply the degree measure by pi over 180 degrees. And you could see how this would work, where if I wanted to say, figure out what, I don't know, 150 degrees is in radians, I could set up a proportion. Okay, and where x would be the angle in radians, and you could see that I'd end up having to multiply by pi on each side of the equation here. So essentially I'm ending up having to multiply by pi over 180 degrees to convert from degrees to radians. And then the same thing for if I want to go from radians to degrees, I would need to set up a proportion, and I end up essentially multiplying the angle that's in radians by 180 degrees over pi. So just a little practice. If we want to go from 60 degrees to radians, so I have 60 degrees, and I would multiply by pi over 180 degrees. So we can think about the degrees as canceling. This was an angle that was just on the unit circle, right? So that's equivalent to pi over 3. and 460 degrees to radians. That would end up being 23 pi over 9. And now for an angle to be in radians, it doesn't have to have pi. For example, if there's an angle equal to 2 radians or 3 radians, it doesn't need to have pi, but when you see a pi in there, you see no degree symbol, usually when you see pi, it's an angle that is being measured in radians. Okay, so we want to go from 3 pi over 2 to degrees. That's also an angle that's on the unit circle, but let's do the conversion. So I'm going to multiply by 180 degrees over pi. Notice the pi's will cancel. We'll have 3 times 9D, which is 270 degrees. And then to evaluate the trig functions for theta and radians, again, using our unit circle, we can look at, for sine of 2 pi over 3, we can go to our unit circle and look at the angle 2 pi over 3, and then the y value. So sine of 2 pi over 3 is equal to root 3 over 2. Cosine of 5 pi over 4. Well, I know it's going to be either root 2 over 2 or negative root 2 over 2. 5 pi over 4 lies in quadrant 3, right? Because 4 pi over 4 would be pi. And then cosine is going to be, remember all students take calculus. So in quadrant 3, cosine is negative. So it's going to be negative root 2 over 2. And let's double check that on the unit circle. So 5 pi over 4, negative root 2 over 2. And then tangent of pi, tangent is, remember, sine over cosine, so y over x. So on the unit circle, pi has the point -1, 0, so that would be 0 over -1, which is just 0. Let's double check up here. Oh, I almost forgot. Okay, so we're not done. So this year, besides on our unit circle having all the points and the angles filled in, we're also going to fill in tangent around the unit circle for each point. Okay, so it'll be really helpful for you guys. Remember, I said you need to be really fast with evaluating the trig functions for angles that lie on the unit circle. So tangent, remember, is sine over cosine, which means y over x on the unit circle. So 1/2 over root 3 over 2 is going to give us root 3 over 3. Root 2 over 2 over root 2 over 2 would give us 1. And then root 3 over 2 divided by 1/2 will give us root 3. 1 divided by 0 is undefined. Okay, and then now we can use symmetry. So this will be negative root 3, -1, negative root 3 over 2. 0 over -1 is 0. Oh, that's not root 3 over 2, it's root 3 over 3. Negative root 3 over 3. Okay, root 3 over 3, right? Because -1/2 divided by negative root 3 over 2. Positive 1. Positive root 3. Undefined. Negative root 3. -1. And negative root 3 over 3 and 0. So in green is all of the values for tangent. And then remember, as a check, all students take calculus. So that tells us, remember, which trig functions are positive in each of the quadrants. So in quadrant 1, all 6 trig functions are positive. In quadrant 2, sine and its reciprocal cosecant are positive. In quadrant 3, tangent and its reciprocal cotangent are positive. And in quadrant 4, cosine and its reciprocal secant are positive. Okay, so all of the values of tangent, all the points around the unit circle, and all the angle measures and radians and degrees you need to memorize.